All right, welcome. Today we are cracking open the instruction manual for the universe itself. We're going to learn the language of physics, a way to actually see the elegant, simple rules that are hidden all around us in plain sight. Let's jump right in.
So you got to wonder, right? How do we do it? How do we take all the mess and complication of reality and somehow pull out clear patterns that we can actually understand and even predict? The secret, and this is the cool part, isn't about being some kind of math genius. Nope. It's about learning to read and speak a very special language, one that's built on the simple beauty of numbers and shapes.
And that leads us straight to our first big idea. For today, let's just stop thinking about physics as a pile of scary formulas. Instead, let's start seeing it for what it truly is. It's a language. A language designed specifically for describing reality. And just like any other language, it's got its own vocabulary and it's got its own grammar.
The basic vocabulary here isn't words like nouns and verbs. It's measurements. It's data. These are the fundamental building blocks we use to describe the world, creating a direct link between one physical thing and another. You can think of them as the simple, essential words we have to learn before we can even begin to build a sentence. But, a list of words isn't a story, right? To actually see the patterns, to see the relationships that are hiding inside all that data, we need to turn that data into a picture. We need to make it visual.
We usually start with something that looks a lot like this, a simple table. This is how we organize our vocabulary. On the left, we've got the side length of a square. Over on the right, its perimeter. Now, the table does a pretty good job of showing the relationship. As one number changes, the other one changes right along with it. But we can do so much better.
We bring this table to life using a graph. All we do is draw a horizontal x-axis for our side length and a vertical y-axis for the perimeter. And bam, we've created a canvas. Now, each one of those pairs of data from our table becomes a single specific point on that canvas. And this is where the magic really starts to unfold.
Think about it. Each of these points has its own unique address. Its coordinates. It's just like a location on a map. Every single data point now has a precise XY position that tells us exactly where it lives. This is what allows us to go from just a boring list of numbers to a real visual story.
Because once we plot all our points, they don't just sit there all random and chaotic. They form shapes. And these shapes, well, they are the grammar of our language. They tell the story of the relationship between our two quantities. They actually reveal the underlying rule.
So let's read our first story. This one's called direct proportionality. And it's the simplest relationship you can find. When one thing goes up, the other thing goes up by a predictable constant amount. If you double one, you double the other. It's that simple. Their ratio stays exactly the same. And the visual signature for this story? It's unmistakable. It is always a straight line that goes right through the starting point, the origin. I mean, look at our square example. A side length of 2 gives a perimeter of 8. A side length of 4 gives a perimeter of 16. When we plot those points, we get a perfect, clean, straight line. That shape is the story.
But hey, not all stories are so straightforward, are they? Let's consider the total opposite, inverse proportionality. Here, the relationship is like a seesaw. As one quantity gets bigger, the other one systematically gets smaller. Just think about driving 100 miles. The faster your speed, the less time your journey takes. In this case, it's their product that stays constant.
And its signature shape is completely different. It's this beautiful downward swooping curve called a hyperbola. It starts up high and then it gets closer and closer to that bottom axis, but never actually touches it. The moment you see that curve, you instantly know you're looking at that seesaw relationship, where one thing's gain is always another's loss.
Okay, now for our third and maybe our most dramatic relationship, quadratic proportionality. This describes situations where one quantity doesn't just grow along with another, it accelerates, it explodes, it grows in proportion to the square of the other. So if you double one variable, the other one doesn't just double, it quadruples.
And its shape is just as dramatic, a powerful upward sweeping curve called a parabola. The area of a circle is a fantastic example of this. As you increase the radius just a little bit, the area grows much, much faster. This sharp, U-shaped curve is the visual fingerprint of that kind of powerful, accelerating growth.
So we can read this story from its shape.
That's a huge step. But the real power of this language isn't just in describing what is. It's about asking questions, finding the unknown, and predicting what will be. And this is where the sentence of our language, the equation, really comes into play.
Let's test this out with a classic riddle. Now, it sounds like a tricky brain teaser, but it's really just a sentence that's waiting to be translated into the language of physics. If we just let x be the unknown total weight of the brick, we can turn this confusing word problem into a simple, solvable equation.
So how do we solve it? We use this fundamental rule, the first principle of equivalence. Just think of an equation as a perfectly balanced scale. Our sentence becomes x equals 1 kilogram plus half of x. Now, to keep that scale balanced, let's take half of x off the right side. That means we absolutely must take half of x from the left side too. What's that leave us with? Well, half of x is on the left and 1 kilogram is on the right. And if half the brick weighs 1 kilogram, the total weight has to be 2 kilograms. See? That one simple rule just gave us the answer.
And what's really amazing is the flexibility you get. A single relationship, one single equation, can be rearranged to answer all sorts of different questions. If you know that speed is distance divided by time, well, you can use that exact same relationship to find the distance if you already know the speed and the time. It's like using the same words, but just rearranging them to ask a different question. That's the whole magic of inverse formulas.
Ultimately, this is not about passing a test. The language of physics is a powerful tool for thinking. It's like a new lens you can use to look at the world, to see the elegant, hidden patterns that connect speed to time, size to area, and, well, so much more.
So I'll leave you with this. Now that you know the basics of the language, now that you can recognize the grammar of reality, that straight line, that downward curve, the upward sweep, what patterns will you start to notice? What hidden relationships are just waiting to be read in the world all around you?